A stone temple has survived violent earthquakes for 1,000 years without any steel. This is the reality of ancient earthquake-resistant architecture, a masterpiece of engineering achieved with only stone, wood, and profound ingenuity. By the end of this, you will see ancient structures not as ruins, but as a forgotten textbook for building a safer world. How did builders make rigid stone dance with the shaking earth? What hidden principles allowed pagodas to sway and Inca walls to settle without falling? The answers lie in a fusion of physics, culture, and a deep harmony with nature that we are just beginning to decode. What does true resilience look like when you have to build it from the ground up? The paradox is as stark as the stone itself. How can a structure made from heavy, rigid blocks be designed to move? For ancient builders, this was not a theoretical puzzle but a daily reality. Their homes, temples, and cities were often founded directly atop the Earth's most restless regions. The Roman Empire straddled seismic faults that run like fractures through Italy. The Inca heartland was cradled by the grinding collision of tectonic plates that built the Andes. In Japan, the very ground was understood to be a living, shifting entity. This constant, looming threat of the earth shaking was not just a hazard, it was a fundamental design constraint. It meant that every architectural choice from the foundation up was made with an invisible opponent in mind. These cultures didn't have the luxury of ignoring the problem. Their survival and the legacy of their civilization depended on solving it, so they turned their greatest vulnerability into their most profound strength. They learned to listen to the earth, to understand its language of tremors and shifts, and to build in conversation with it. The goal shifted from resisting force to managing it, from building walls that would stand stiff against a quake to creating systems that could absorb, redirect, and dissipate that incredible energy. And they had to do it all with the simplest toolkit imaginable. No steel cables to provide tensile strength, no rubber isolation pads, no computer models. Just stone shaped by hand, timber harvested from the forest, clay mixed with straw, and an accumulated wisdom passed down through generations of trial, observation, and sometimes catastrophic error. This wisdom led them to principles that seem counterintuitive today. They discovered that a building that is too rigid is a building doomed to crack. Instead, they sought a kind of flexible integrity. Think of it not as a fortress bracing for a blow, but as a tree in a storm. Its roots hold fast, its trunk sways, its branches give way to the wind. The structure survives not by being unbreakable, but by being smart enough to bend. This is the foundational mystery we are about to unravel. How did they engineer this flexibility into stone? The first clues are found not in the walls but beneath them. The master stonemason's hands move with a patient rhythm, feeling the granite's grain. In the highlands of ancient Peru, under a vast sky, this artisan is not just building a wall, he is solving a monumental puzzle without a single drop of mortar. This is the art of dry stone masonry, and it represents the first, most fundamental principle of seismic resilience. The goal was not to glue stones together permanently, but to fit them in a state of perfect dynamic tension. Each block was painstakingly shaped, its neighbors carefully chosen, so that they locked together with interlocking protrusions and recesses. It was a three-dimensional jigsaw puzzle carved from the living earth, where every piece relied on the pressure and geometry of those around it. This created something far more sophisticated than a solid wall. It created a unified yet flexible mass. When the ground shook, these meticulously fitted stones could do something miraculous. They could shift, they could grind against one another, they could settle into a slightly new position. The energy of the earthquake was not absorbed by a single, rigid point until it shattered, but was dissipated across countless surfaces through friction, as the entire structure subtly reorganized itself. As experts like Dr. John Otzendorf have illustrated, this is a profound understanding of physics in action. The builders intuitively knew how to manage both static loads, the constant weight of the structure, and dynamic loads, the sudden, violent forces of a tremor. They engineered a system that could accommodate movement, a concept modern engineers term a seismic design, but which these artisans understood through touch, sight, and generations of hard-won knowledge. This was seismology written in stone long before the science had a name, and if the foundation could move, what about the structure it supported? The next leap in ancient engineering was even more daring, creating buildings that didn't just settle, but actively swayed with the quake's rhythm. High above the ground, a wooden pagoda dances with an earthquake. While the Inca mastered the art of shifting stone, builders in Japan and China confronted the same violent forces with a different, brilliant solution. They turned to the forest, engineering a second principle of ancient seismic wisdom, the strategic use of flexibility with timber. Here, rigidity was the enemy, and the goal was to build structures that could sway, absorb, and return to center, much like a deeply rooted tree. The iconic multi-tiered pagoda is the perfect example. To the eye, it appears as a stack of heavy roofs, a tower that should topple at the first serious tremor. Yet for centuries, these pagodas have survived tremors that flattened modern concrete buildings around them. Their secret lies in a hidden skeleton of wood, assembled with such ingenious joinery it seems almost alive. The core of this system is a massive central pillar, often made from a single, towering tree trunk. But this pillar is not anchored into the foundation. Instead, it hangs suspended from the upper levels of the structure, acting as a giant, weighted pendulum. When the ground shakes, the building sways around this independent, swinging core. The heavy eaves of each roof tier act as stabilizing masses, while the wooden frame connecting them is designed to flex. This is where the artistry of the carpenter becomes pure physics. They used complex interlocking brackets, joints carved to fit together without nails or glue. These joints, known as Tokyo in Japanese tradition, are not rigid locks. They are carefully calibrated connections that allow for controlled movement. They compress, they twist, they slide just enough to dissipate energy. As architectural historian Professor Akira Nato has described, the entire structure becomes a dynamic system. The flexible frame and the heavy roof masses work in opposition, creating a damping effect that counteracts and neutralizes the seismic waves passing through it. It is a form of organic engineering, a biomimetic approach crafted 1,000 years before the term was invented. The builders observed how bamboo bends in a storm and replicated that resilience on a monumental scale. They understood that to defeat the earthquake, you must first learn to move with it. This philosophy of flexible integrity, whether in Peruvian stone or Japanese timber, points to a unifying insight. But what about the very earth these structures stood upon? The final and perhaps most subtle principle of ancient seismic design was not in the building itself, but in the ground it touched. Beneath the swaying pagoda and the shifting stone wall lies the most critical layer of all, the ground itself. Ancient builders grasped a profound truth that modern engineering confirms. A structure is only as stable as what it stands upon. Their third principle of seismic wisdom was not about building something strong, but about preparing a foundation that could remain dependable when everything else was shaking. This was the genius of the invisible foundation, a masterclass in proactive ground engineering. In the floodplains of Mesopotamia, where the earth was soft and unstable, builders laid down thick mats woven from reeds beneath their brick structures. This simple, brilliant innovation acted as a flexible raft, distributing the building's weight over a wider area and absorbing minor, constant shifts in the wet soil. It prevented differential settlement where one corner sinks faster than another, a common cause of catastrophic cracking. They were, in essence, giving the Earth a firm handshake, creating a stable interface between the human-made and the natural world. Far to the east, in the meticulously planned cities of the Indus Valley, engineers confronted a different subterranean threat: liquefaction. During intense shaking, water-saturated soil can lose its strength and behave like a liquid, causing structures to tilt and sink as if into quicksand. The ancient solution was both elegant and effective. They constructed sophisticated networks of baked clay drains and laid foundations of carefully compacted gravel. This system did two things. It provided immediate drainage to keep the soil from becoming oversaturated, and it created a rigid, load-bearing base that could bridge over weaker layers below. They weren't just building on the ground, they were actively engineering the ground to be a reliable partner. This concept of making the Earth itself part of the defensive system is a cornerstone of modern geotechnical engineering, yet it was practiced with astonishing foresight thousands of years ago. It reflects a holistic understanding that resilience is a dialogue between structure and site. The true strength of their architecture often resided in what was deliberately hidden from view, a prepared and stabilized Earth that could bear the load when the world began to tremble. But these three principles, flexible masonry, dynamic timber frames, and engineered foundations, were not isolated tricks. They point to a deeper, more unifying source of knowledge, one that connected the builder not just to materials, but to the very patterns of the natural world. The most resilient structure is not one that never breaks, but one that knows exactly where to break. This is the fourth, and perhaps most counterintuitive, principle of ancient seismic wisdom: the deliberate design of controlled weak points. In the quest for survival, ancient builders understood that sometimes you must sacrifice a part to save the whole. They engineered specific, calculated fragilities into their monuments, guiding the chaotic force of an earthquake down a predetermined, less destructive path. In the grand basilicas of the Byzantine Empire and the soaring mosques of the later Ottoman world, we find evidence of this brilliant foresight. Builders would often mix their mortar with unusual additives, creating a more flexible, almost rubbery binding agent between stones. More strikingly, they would sometimes insert horizontal beams of wood directly into the stonework at critical junctures, like the corners of arches or the tops of walls. To a modern engineer inspecting a static building, these wooden layers might look like a flaw, a point of vulnerability, but during a seismic event, they become the structure's secret weapon. When the ground heaves, these designated areas are engineered to fail first. The flexible mortar crumbles in a controlled manner, or the wooden beams compress and deform. This intentional cracking acts as a release valve, absorbing and dissipating massive amounts of destructive energy. It channels the earthquake's fury away from the primary load-bearing walls and columns, the vital skeleton of the building. The concept is strikingly similar to a fuse in an electrical system. When a power surge hits the fuse, a deliberately weak link burns out to protect the entire circuit from catastrophic damage. Ancient architects were installing seismic fuses into their stone and brick centuries ago. This required a deep, almost prophetic understanding of how their buildings would behave under extreme stress. They had to visualize the invisible pathways of force flowing through arches and vaults, predicting exactly where stress would concentrate. By creating a planned failure point at that precise location, they turned a potential catastrophe into a manageable event. A cracked section of mortar or a deformed wooden beam could be repaired. A collapsed dome or a shattered column could not. This philosophy reflects a mature acceptance of nature's power, a strategic retreat that wins the larger war for preservation. It moves beyond simple resistance into the realm of intelligent energy management, proving that true strength often lies in knowing precisely when and how to yield. Sheer weight can become a shield against chaos. This is the fifth principle, where ancient builders mastered the physics of mass, using inertia not as a burden, but as a strategic tool for stability. Think of the colossal stone blocks of an Egyptian temple gateway or the thick, towering walls of a Romanesque cathedral. These are not merely displays of power, they are calculated seismic defenses. By constructing with such immense, dense materials, the builders were increasing the structure's inertia, its resistance to changes in motion. High-frequency seismic waves, the sharp, jolting tremors that can shatter brittle materials, meet their match in a multi-ton stone block. It simply takes too much energy to set that much mass quickly into motion. The building, in essence, refuses to dance to the earthquake's most violent, rapid rhythm. It stands as a stoic giant, letting the high-frequency energy pass around and beneath it, unable to get a proper grip, but mass alone is a blunt instrument. The true sophistication came in how they orchestrated that weight. Builders often incorporated heavy architectural elements, like ornate roof combs, parapets, or the heavy timber and tile work of a pagoda's eaves in very specific positions. These elements were not just decoration, they became dynamic counterweights. During a quake, as the main structure began to sway, these heavy upper features would lag slightly behind due to their own inertia, then swing with a momentum of their own. This created a damping effect, where the movement of the counter mass worked to oppose and cancel out the movement of the building itself. It was a primitive, yet brilliantly effective, form of what modern skyscrapers use today, a tuned mass damper. In contemporary engineering, this is often a gigantic steel ball suspended near the top of a tower, programmed to sway in the opposite direction of the wind or seismic forces. Ancient builders achieved a similar result through architectural intuition, placing mass strategically to create a system of balanced opposition. They turned the building into a self-regulating entity, where one part's movement naturally checked another's. This principle reveals a deep, almost instinctual grasp of dynamic equilibrium. They understood that stability in the face of chaos is not a static condition, but an active state of balance, a continuous, silent negotiation between opposing forces. It is engineering as a form of philosophy, where weight is given purpose and movement is met with an equal and opposite intention. Yet, for all these mechanical insights, the most profound element of their success may have been something less tangible, a cultural wisdom written not in stone, but in memory and tradition. Geometry was their silent guardian against chaos. Step back and admire the perfect, mirrored symmetry of a Greek temple, its columns standing in flawless rows, or the stepped majesty of a Mayan pyramid, each side an identical reflection of the other. This visual harmony is far more than an aesthetic choice. It is the sixth principle of ancient seismic wisdom, a profound application of geometric order as a structural defense. Symmetrical designs are inherently stable because they distribute weight and force evenly. When an earthquake's energy hits a perfectly symmetrical structure, it has no weak flank to target, no unbalanced corner to exploit. The seismic waves are met with equal resistance from all sides, forcing the energy to travel through the entire framework rather than concentrating at a single, vulnerable point. This principle of even distribution prevented the catastrophic stress concentrations that cause modern, asymmetrical buildings to twist and buckle. But the ancient mastery of geometry went far beyond simple symmetry. Builders employed complex, repeating patterns that acted as sophisticated force dissipation networks. In the breathtaking tilework of Islamic architecture, the intricate honeycomb patterns of Muqarnas vaulting are not merely decorative. These interlocking geometric cells create a three-dimensional lattice that channels forces along countless, redundant paths. If one cell deforms under stress, the surrounding cells immediately share the load, preventing a local failure from becoming a global collapse. It is nature's own engineering, mirrored in stone and plaster, the same structural logic found in a beehive or a sponge. Similarly, the Inca preference for trapezoidal shapes for doors, windows, and niches was a stroke of seismic genius. A rectangle under lateral force wants to deform into a parallelogram, its corners straining at sharp, weak 90-degree angles. A trapezoid with its sloping sides inherently resists this deformation. The shape guides forces downward toward the wider base, funneling energy safely into the foundation. As the Peruvian architect and historian Santiago Agurto Calvo emphasized, this was not accidental beauty. It was a calculated, mathematical application of principles to achieve structural equilibrium. Every angle, every proportion was a variable in an equation for survival. They turned sacred geometry into a life-saving science, understanding that the most resilient forms in nature are often those built from repetition and balance. The patterns in a spider's web, the hexagonal basalt columns of a cooling lava flow, the spiral of a nautilus shell, all manage force with elegant efficiency. Ancient builders observed these natural blueprints and codified them into their art, creating structures where form and function were indivisible. The temple was not just a place of worship, it was a physical prayer for stability, its very geometry a spoken contract with the forces of the earth. This deep integration of knowledge suggests that their greatest tool was not the chisel or the adze, but a holistic worldview that saw no separation between the practical and the profound. The final, and perhaps most vital, element in this ancient equation was not stone or timber, but time itself. The seventh principle reveals that the true secret to seismic resilience was a cultural one, a slow and sacred accumulation of knowledge passed from one generation of builders to the next. These were not inventions born in a single moment of genius, but solutions refined over centuries through a relentless process of trial, observation, and painful error. When a temple withstood a tremor while others fell, its design became a living lesson. The precise angle of its trapezoidal doorway, the specific pattern of its stone coursing, the unique composition of its foundation mortar, all were carefully noted, replicated, and subtly improved upon in the next project. This was an iterative science, a living database of architectural wisdom written not on parchment, but in the very landscape. Master builders and guilds became the custodians of this knowledge, teaching apprentices through hands-on practice and oral tradition. They understood the behavior of local materials intimately, knowing which quarry produced stone that could flex, which forests grew timber with the perfect balance of strength and give. Each successful structure that endured became a prototype, a three-dimensional blueprint for the future. Its longevity was a silent teacher, proving which principles worked. Conversely, the ruins of a collapse were studied with equal reverence, not as mere failures but as critical data points. They answered the question of what not to do, revealing the limits of a certain arch or the weakness of a particular foundation in that specific type of soil. This long-term, cumulative approach stands in stark contrast to our modern, rapid cycle engineering. We have brilliant materials and powerful computers, but we often lack the centuries-deep feedback loop these ancient cultures possessed. Their resilience was baked into the cultural memory, a collective inheritance that ensured hard-won lessons were not lost but became the bedrock for all that followed. The Pantheon on the Acropolis is not the first temple on that site, it is the culmination. The pagodas of Japan were rebuilt again and again, each iteration incorporating subtle refinements learned from the last quake. This process transformed architecture into a dialogue with the earth that spanned lifetimes, where each generation listened to the whispers of the past to better hear the rumblings of the future. The strength of their walls was ultimately a reflection of the strength of their tradition, a chain of knowledge unbroken long enough to learn the rhythm of the ground itself. The secret to their concrete was not in its strength, but in its ability to heal. While the Inca and Japanese mastered the mechanics of movement, Roman engineers were conducting a quiet revolution in chemistry, creating a material that seemed to defy time and tremor alike. This was not the brittle concrete of modern construction sites, but a living, breathing composite that grew stronger with age, especially when challenged by the restless earth. Their key ingredient was not mined from a quarry, but scooped from the slopes of volcanoes, a fine, sandy ash known as pozzolana. When mixed with lime and water, this volcanic powder triggered a chemical reaction that continues for centuries. Instead of simply drying hard, Roman concrete undergoes a process called pozzolanic reaction, where the ash and lime form microscopic, interlocking crystals. These crystals create a dense, cohesive matrix that is remarkably resistant to cracking. But more importantly for seismic zones, this matrix also possesses a degree of flexibility. Under stress, tiny microcracks can form, but the ongoing chemical activity allows these cracks to slowly self-seal as new crystals grow to bridge the gap. The material could handle the push and pull of an earthquake because it was engineered not as a monolithic slab, but as a dynamic, self-repairing ecosystem on a microscopic scale. Modern Portland cement, by contrast, often sets in a more rigid, brittle state. When it cracks, water infiltrates, rusting the steel rebar inside and leading to catastrophic failure. Roman concrete had no steel to corrode, and its very chemistry was designed to welcome water, using it to fuel further healing. This is why Roman harbors, submerged in seawater for 2,000 years, stand intact while modern concrete piers crumble in decades. The material was so perfectly tuned to its environment that it turned a destructive force, water and seismic movement, into a source of its own longevity. A similar philosophy of intelligent material science flourished across the ancient world. In the monumental temple complexes of South Asia, builders achieved seismic flexibility through a specialized plaster known as cerci. This was a mix of lime and finely crushed brick dust. The lime provided the binder, while the countless tiny, fired clay particles in the brick dust acted as a multifunctional reinforcement. First, they created a rough, porous texture that gave the next layer of plaster something excellent to grip onto, preventing delamination. Second, and more crucially, these hard particles distributed stress throughout the material. When the masonry joints sealed with cerci were subjected to the shearing forces of an earthquake, the plaster could deform slightly without shattering. The brick dust particles would shift minutely within the lime matrix, absorbing energy through friction, much like the shifting stones of an Inca wall, but on a microscopic level. This created a masonry joint that was not a rigid glue, but a flexible, energy-absorbing cushion. It allowed the heavy stone blocks above to move ever so slightly without losing their cohesive bond, preventing the concentration of stress that would cause a catastrophic fracture. These ancient composites reveal a fundamental shift in how we view their technology. They were not just mixing dirt and water, they were nano-engineers before the concept existed. They empirically discovered formulations that balanced compressive strength with tensile flexibility, creating materials that were in dialogue with the forces they faced. Their concrete could heal, their plaster could flow. They built not for a static ideal of permanence, but for a dynamic reality of movement and repair. This material wisdom, combined with the geometric and structural principles we've seen, forms a complete architectural language. But to hear it spoken, we must look at the ultimate test, the structures that have stood for centuries in the planet's most violent seismic zones. Machu Picchu is a perfect storm of ancient seismic principles in action. This iconic city, clinging to a knife-edge ridge in the Peruvian Andes, sits directly within one of the most seismically active regions on the planet. Its continued existence through centuries of violent mountain tremors is not a matter of luck. It is the result of every principle we have discussed being applied with breathtaking precision and scale. Here, the abstract concepts of flexibility, drainage, and mass become a tangible, walkable reality. the journey begins with its very foundations. The Inca did not simply flatten the mountain ridge to build upon it. Instead, they performed a kind of geological surgery. They excavated down to the solid bedrock, then built back up with layer upon layer of precisely graded stones and gravel. This created a deep, engineered foundation that served multiple critical functions. It provided a stable, load-bearing platform that could bridge over any minor weaknesses in the underlying rock. More importantly, these deep layers formed a colossal drainage system. Water from the relentless mountain rains and mist would percolate down through the stonework, channeled away from the structure's base. This prevented the nightmare scenario of liquefaction, where water-saturated soil turns to fluid under seismic shaking, causing entire sections of the city to slide down the mountainside. The foundation itself was a first line of defense, a subterranean architecture of stability. Upon this prepared base, the masons executed their masterwork, the polygonal walls for which Machu Picchu is justly famous. These are not simple rows of rectangular blocks. Each stone is a unique, irregular polygon, shaped over countless hours to fit perfectly with its 5, 6, or 7 neighbors. The joints are so tight that, as the saying goes, not even a blade of grass can slip between them. This is dry stone masonry elevated to an art form. But the true genius is in the wall's internal structure. The stones are not all the same size. Larger, more massive blocks form the base and critical corners, while smaller stones fill the spaces above. This creates a graduated mass distribution, lowering the center of gravity and increasing the structure's inertial resistance to shaking. When an earthquake strikes, these interlocking polygons can minutely shift and grind against one another. The energy is dissipated as friction across thousands of intricate stone faces, rather than being focused into a single, catastrophic fracture line. The entire wall settles like a slow, deliberate dance, then locks back into place. As archaeologist Kenneth Wright's meticulous studies revealed, the integration with the landscape is total. Key structures are often built directly onto and around outcrops of living bedrock, using the mountain itself as a permanent anchor. But perhaps the most expansive seismic feature is the one that defines the city's silhouette, the agricultural terraces. These are not just fields for growing crops, they are giant, stepped retaining walls that grip the entire mountainside. Each terrace is a complex, layered construction with stone facing, a drainage layer of gravel, and rich topsoil. Collectively, they act as a massive net, stabilizing the steep slopes against landslides triggered by seismic activity. They prevent erosion and hold the very mountain together, making the site itself more geologically sound. Machu Picchu, therefore, is not a city placed upon a mountain. It is a city woven into the mountain. Its architecture and the environment are a single, interdependent system for survival. Every terrace, every drain, every uniquely shaped stone is a word in a silent conversation with the earth, a conversation about resilience written across an entire ridge line. This holistic approach raises a profound question. If these principles were so effective, why did this deep, intuitive knowledge seem to fade from our collective architectural memory for so long? The 5-story pagoda at Horyuji Temple is a silent witness to 14 centuries of earthquakes. It stands not because it is rigid, but because it was designed to sway with a kind of graceful, calculated purpose. At the heart of this ancient wooden tower lies its most brilliant secret, a single, massive pillar called the Shinbashira. Unlike every other support in the building, this central column does not rest on the foundation. It hangs freely from the upper levels, suspended like a giant, weighted pendulum in the very core of the structure. This is the dancing column, and it transforms the entire pagoda into a dynamic seismic instrument. When the ground begins to shake, the building's flexible wooden frame starts to sway, but the heavy, hanging Shinbashira, due to its inertia, initially lags behind. It then begins to swing in the opposite direction to the floors around it. This creates a phenomenon known as a damping effect, where the movement of the central mass actively counteracts and neutralizes the movement of the building itself. The energy of the earthquake is not met with a wall, but is absorbed into this silent, rhythmic opposition between the tower and its suspended heart. As Professor Akira Nato's research illuminates, this is not a static post but a dynamic participant. The Shinbashira dances, and its dance steadies the entire form. This principle works in perfect harmony with the intricate joinery of the timber frame. Those complex, interlocking brackets are not nails or glue. They are carefully calibrated connections that allow for just enough give. They compress and flex, acting as shock absorbers that distribute the strain. Together, the flexible joints and the dancing column create a system of extraordinary resilience. The pagoda does not fight the earthquake's energy. It accepts it, channels it, and allows it to dissipate harmlessly through movement. It is a masterpiece of pre-modern engineering that understood a truth we are still relearning today, that true stability in a chaotic world is not found in absolute rigidity, but in intelligent, controlled flexibility. This ancient insight, carved in wood and perfected over a millennium, speaks to a philosophy of building that sought harmony with natural forces, creating structures that were not just shelters, but partners in a dynamic conversation with the earth. Its dome is a perfect hemisphere of unreinforced concrete, a material we associate with cracking and collapse. Yet the Pantheon in Rome has not only survived for nearly 2,000 years, it has endured in a region of known seismic activity. This is the Roman case study in seismic resilience, a testament to engineering that thought in layers, both visible and hidden. The secret was not in making the concrete stronger in a conventional sense, but in making it smarter. Roman engineers approached the dome not as a single, monolithic mass, but as a carefully graduated structure. They understood that the greatest threat to such a vast span was its own weight, especially during the lateral shaking of an earthquake. So they engineered the dome's very substance to change from bottom to top. At the heavy, supporting base, the concrete aggregate was mixed with dense, solid stone, providing immense compressive strength to bear the load. But as the dome rose and curved inward, the recipe changed. The stone aggregate was replaced with lighter, porous materials like pumice, a volcanic rock filled with air pockets. This dramatically reduced the overall weight of the upper dome, lowering the stress on the lower walls and minimizing the deadly downward and outward thrust that could cause a catastrophic failure during a tremor. They further lightened the load through brilliant architectural design. The iconic coffered squares carved into the dome's interior are not merely decorative. Each indentation removed tons of unnecessary concrete, turning a solid, oppressive mass into a latticed, efficient shell. This was weight management as a precise science, sculpting the dome to carry only what was structurally essential. But perhaps the most ingenious feature is one visitors never see. Encircling the very base of the dome, hidden within the thick concrete, is a continuous ring of brick. This was not ordinary brickwork. It was a tension ring, a band of flexible, fired clay that acted like a hidden belt holding the entire dome together. Concrete is phenomenally strong under compression, being squeezed, but notoriously weak under tension, being pulled apart. During an earthquake, the dome would experience powerful tensile forces trying to pull it outward. The embedded brick ring, with its greater flexibility and tensile strength, absorbed these forces. It allowed the structure to flex minutely without developing the large cracks that would shatter pure concrete. This combination of graduated materials, intelligent lightening, and hidden reinforcement reveals a holistic philosophy. The Romans did not rely on a single trick. They combined material science, architectural form, and concealed structural elements into a single, resilient system. The Pantheon stands not as a monument to rigid permanence, but to flexible, layered intelligence, a concrete testament to building in conversation with the very forces that seek to tear things down. A temple stands on a bed of flowing sand. In the seismic landscapes of ancient India, where the earth's restlessness was woven into spiritual law, builders confronted a foundational challenge. How could they erect a massive, intricate stone temple, a symbol of cosmic order, upon ground that threatened to turn to chaos? Their answer was both elegantly simple and scientifically profound, a technique modern engineers now recognize as a primitive but brilliant form of base isolation. They called it the Sandbox Foundation. The process began with a deep excavation, a pit carved into the earth below the proposed temple site. But instead of filling this cavity with more packed earth or rigid stone, they lined it with a thick layer of loose, dry sand or fine gravel. Upon this deliberately unstable bed, they would then begin constructing the temple's heavy stone plinth, its massive walls and its soaring towers. To the static eye, this seems counterintuitive, even reckless. Why place a monument of eternal aspiration on a foundation designed to shift? The wisdom reveals itself only when the ground begins to move. During an earthquake, the seismic waves travel upward from the bedrock. When they hit the layer of sand, something remarkable happens. The granular material does not transmit the shaking directly. Instead, the individual particles roll and slide against one another, absorbing and dissipating a tremendous amount of the energy through friction. The entire stone structure above is in effect floating on this fluidized layer. It can settle, tilt, and even rotate slightly as the sand beneath it flows and re-levels itself. This movement is slow, distributed, and crucially, it is decoupled from the violent, high-frequency jerking of the earth below. The temple sways as a single, unified mass on its granular cushion, rather than having its rigid stone joints subjected to shearing forces they cannot withstand. The superstructure remains largely intact because the foundation itself becomes a shock absorber. It is a concept of breathtaking foresight, isolating the building from the very ground it stands upon. This ancient sandbox principle finds its direct descendant in the base isolation systems of contemporary skyscrapers and hospitals. Today, we use sophisticated layers of rubber and steel bearings, but the core idea is identical: to create a flexible interface that lets the ground move independently of the structure. The Indian temple builders achieved this with nothing more than sand, gravity, and a deep understanding of material behavior. This technique speaks to a holistic philosophy of construction, where every element, even the earth itself, was intentionally engineered to play a specific role in a dynamic system of survival. The temple was not just built on the land, it was designed in intelligent partnership with the land's most volatile nature. These principles of flexibility and mass were not born in the Age of Empires, but forged much earlier in the fires of the Bronze Age. Beneath the sun-bleached stones of the Aegean, the very first European civilizations were already writing the opening chapters of seismic design. On the island of Crete, the sophisticated Minoans built not just palaces, but labyrinths of stone engineered to withstand the shaking of their island home. Their signature technique was a brilliant fusion of materials known today as half-timbering. They would construct walls using precisely cut, rectangular stone blocks called ashlar masonry, creating a sturdy, orderly facade. But the true genius was hidden within the wall's core. At regular intervals, the masons would leave long, narrow channels running horizontally through the stonework. Into these channels, they would insert sturdy wooden beams, often of cypress or oak, locking them into place. This simple insertion transformed the entire wall's behavior. Stone is incredibly strong under compression, but brittle when bent or twisted. Wood, however, possesses a natural tensile strength, an ability to flex and stretch without snapping. During an earthquake, the wooden beams acted like a flexible skeleton within the stone shell. They could bend and absorb the lateral forces, preventing the rigid stone blocks from cracking apart at the joints. The wall became a composite material, each component doing what it did best, the stone bearing the vertical load, the wood managing the horizontal shock. It was an early, masterful application of what engineers now call reinforced masonry, a concept we think of as modern, yet practiced with intuitive brilliance over 3,000 years ago. Meanwhile, on the Greek mainland at mighty Mycenae, a different, more monumental approach to seismic safety was taking shape. Here, builders employed what later Greeks would call Cyclopean masonry, named for the mythical giants, the Cyclopes, who they believed must have been the only beings strong enough to lift such stones. These were not precisely cut blocks, but enormous, irregular boulders of limestone, some weighing many tons. The builders would carefully select each boulder, shaping its contacting faces to interlock tightly with its neighbors, filling the gaps with smaller stones and clay. The stability here came from sheer, overwhelming mass and a perfect, puzzle-like fit. The incredible weight of the walls gave them immense inertia, making them resistant to being shoved off their foundations by seismic waves. More importantly, the complex, interlocking shapes of the boulders created a three-dimensional jigsaw. When the ground shook, these gigantic stones could shift and settle against one another, dissipating energy through friction along their countless, irregular contact points. The entire fortification wall would settle as a unified, flexible mass, rather than collapsing as a pile of rigid blocks. These Bronze Age ruins are not merely relics of a lost world, they are active archaeological classrooms. The patterns of collapse and survival in sites like Knossos and Mycenae provide clear evidence. Walls that incorporated wooden beams often show less catastrophic failure, with sections still standing aligned, while purely stone constructions nearby are more thoroughly shattered. This tells a powerful story of continuous adaptation. Architectural styles in these seismic hotspots did not evolve solely for beauty or prestige. They evolved as direct, pragmatic responses to the tremors of the earth. Every innovation in stone cutting, every choice of timber, was a data point in a centuries-long experiment in survival. The Minoan half-timbering and the Mycenaean Cyclopean walls represent two foundational branches on the tree of seismic engineering, one seeking flexible reinforcement, the other relying on intelligent mass. They prove that the conversation between human ingenuity and the restless earth began not as a whisper, but as a determined shout, echoing from the deepest foundations of our architectural history. We can now see the stones shift in slow motion. The precise tilt of a trapezoidal doorway, the subtle give of a wooden bracket, the way a loose sand foundation settles. These were once invisible acts of genius witnessed only in the violent instant of a tremor. Today, we are no longer limited to studying the silent aftermath. A powerful collaboration between archaeology and modern engineering is allowing us to replay these ancient seismic dances, frame by digital frame, and finally understand the mechanics behind the mystery. The tools for this new kind of historical forensics are as precise as they are revealing. Three-dimensional laser scanning can capture every contour, every imperfection of a structure like the Parthenon or a Peruvian temple complex, creating a point cloud model accurate to within millimeters. This digital twin becomes a perfect laboratory specimen. Engineers then employ a technique called finite element analysis. In essence, they break this digital model down into millions of tiny, interconnected virtual elements like a hyper-detailed mesh. They assign material properties to each element based on studies of the actual stone, mortar, or timber. Then they apply the physics. They simulate the exact ground motions recorded from real earthquakes in that region, feeding those complex waves into the digital foundation. What happens next is a revelation. The computer calculates how every single one of those millions of elements reacts. It shows, in vivid color-coded stress maps, exactly where force concentrates and, crucially, how it flows. We can watch a simulation of Machu Picchu's polygonal walls as a seismic wave passes through. The model reveals how stress diffuses across the intricate network of joints, avoiding catastrophic hotspots. It visualizes the Shinbashera column in a Japanese pagoda beginning its counter-sway, damping the building's oscillation. This process validates the intuitive principles we've observed, but it often goes further, uncovering hidden subtleties. An analysis might show that a certain irregular stone in an Inca wall isn't irregular by accident. Its unique shape is perfectly engineered to redirect force toward a larger, more stable block below. It can reveal that the specific angle of a trapezoidal window isn't just aesthetically pleasing. It's the optimal angle to prevent a crack from propagating upward during lateral shaking. This isn't guesswork anymore, it's computational proof. We are stress testing history itself, and the results confirm a sophisticated, empirical science. This fusion of disciplines is doing more than just explaining the past. It is actively inspiring the future. The principles decoded from these ancient sites, principles of flexibility, damping, and energy dissipation, are directly informing cutting-edge seismic research. Modern engineers studying base isolation systems look to the concept of the Sandbox foundation. The design of tuned mass dampers in skyscrapers echoes the pendulum logic of the hanging pillar. By digitally deconstructing these ancient masterpieces, we are recovering a lost manual of resilience, one written in geometry and material behavior. Archaeology provides the artifact, engineering provides the language to read it. Together, they are translating a silent, centuries-old conversation between human ingenuity and the moving earth, allowing us to finally hear the wisdom in the stones. There is a profound irony in our modern quest for seismic safety. We build with reinforced concrete, a material that seems to embody ultimate strength. At its heart lies a partnership, steel providing flexible tensile strength to hold the brittle concrete together. This union created the modern city, allowing us to build higher and faster than ever before. Yet in the face of a truly massive earthquake, this very partnership can become a fatal flaw. The steel inside, called rebar, is vulnerable. Intense, prolonged shaking can cause it to buckle and deform. Worse, if cracks form in the concrete cover, moisture and salt seep in, leading to a silent, insidious process called corrosion. The steel rusts, expands, and from the inside out, it literally blows the concrete apart. This failure is often sudden and catastrophic, a pancake collapse where floors pile atop one another, leaving little chance for escape. It is a stark reminder that raw strength, when it is rigid and brittle, can betray us. Now hold that image and look back at the ancient stones. Their materials were undoubtedly weaker in pure tensile strength. A block of limestone cannot stretch like steel. But that perceived weakness guided their entire philosophy of design, because they could not rely on an invisible metal skeleton to hold everything together. They engineered their structures to fail differently and often more safely. When an ancient dry stone wall was overstressed by a quake, it would not snap. Instead, it would settle. Stones would grind and shift, the structure would tilt, and cracks would open gradually. A timber-framed pagoda would sway violently, its joints groaning, but its flexible skeleton would prevent an instantaneous collapse. This mode of failure is what engineers term ductile or graceful. It provides something invaluable: time. The building announces its distress through visible, audible movement, giving occupants crucial moments to reach safety. It is the difference between a glass pane shattering and a wooden beam bending. One fails without warning, the other signals its distress. This is not to romanticize the past or suggest we abandon the incredible advantages of modern technology. We should not, but it does reveal a critical blind spot in our contemporary approach. We have focused overwhelmingly on material strength, often at the expense of systemic flexibility. We design buildings to meet code, to resist a calculated force, but we seldom design them to manage energy the way a 1,000-year-old temple does. The ancient wisdom suggests a different path forward, not a rejection of steel and concrete, but a hybridization. What if we consciously integrated their principles? Imagine a modern building that uses base isolation, a direct descendant of the Sandbox foundation, to float on flexible bearings. Within its concrete walls, we could engineer deliberate, ductile weak points, modern seismic fuses that sacrifice specific, replaceable components to protect the primary structure. We could design geometric facades that channel force like an Islamic Muqana vault, or use advanced composite materials that mimic the self-healing properties of Roman concrete. The future of resilient architecture may not lie in choosing between ancient intuition and modern science, but in weaving them together. It is about building with the strength of steel, but the wisdom of stone. Creating structures that are not just strong, but intelligently resilient, capable of dancing with the earth when it moves and standing tall when the shaking stops. This hybrid approach asks us to see these ancient sites not as relics, but as active laboratories. Their enduring silence holds answers to questions we are only now learning how to ask. At its heart, every earthquake is a story of energy. A colossal force born deep within the planet travels upward as waves, arriving at the surface with the single-minded purpose of setting everything in motion. A modern building often responds to this command with a rigid refusal, a decision that concentrates all that energy into a few catastrophic points of failure. Ancient builders chose a different path. They designed structures not to refuse the energy, but to politely and systematically ask it to leave. Their genius lay in mastering two fundamental physical principles, friction and inertia, to orchestrate this gentle expulsion. Think of seismic energy as a destructive visitor pounding on your door. You could bar the door with a thick beam, hoping your lock is stronger than their force. That is the rigid approach. Or you could install a sophisticated, spring-loaded hinge that swings inward the moment pressure is applied, guiding the intruder's momentum harmlessly into an empty room before the door swings shut again. That is the ancient, dissipative approach. They turned their buildings into systems of elegant escape routes for energy they could not hope to contain. The dry stone walls of the Inca provide the perfect illustration of friction in action. When a seismic wave hits such a wall, it tries to push the heavy stones laterally to slide them out of place. But each stone is locked in a multi-faced embrace with its neighbors. As the force travels through the wall, it is met not by a single resistance, but by thousands of tiny resistances at every point of contact. The stones grind minutely against one another. In that grinding, the kinetic energy of the earthquake, the energy of motion, is converted into two other forms, heat and sound. The stones warm imperceptibly from the friction, and if you could listen closely during a tremor, you would hear a low, grinding rumble as the energy literally whispers itself away. The wall settles because the energy required to lift and topple massive stones is far greater than the energy dissipated as heat and sound through countless micro-movements. It is a brilliant, distributed defense. Now consider the flexible timber frame of a Japanese pagoda. Here, the primary transformation is different. The building accepts the kinetic energy from the ground and converts it into a different kind of kinetic energy, the large, rhythmic, controlled sway of the entire structure. The joints flex, the heavy eaves swing, and the central column dances in its pendulum motion. This movement is not waste, it is the goal. By allowing the building to move, the energy is gradually transferred from the violent, high-frequency shaking of the earth into the slower, lower-frequency oscillation of the tower. That oscillatory energy then dissipates into the surrounding air as gentle vibrations and wind resistance. It is like pushing a child on a swing. You give a sharp push, kinetic energy, and the child converts it into the smooth, arcing motion of the swing. Eventually, that motion slows due to friction in the chains and air resistance, and the energy is gone. The pagoda is its own swing, designed to turn a sharp, destructive push into a graceful, survivable arc. Then there is the principle of mass and inertia. Inertia is simply an object's tendency to resist changes in its state of motion. A stationary object wants to stay stationary. A moving object wants to keep moving. The massive stone blocks of a Mycenaean wall or an Egyptian pylon possess enormous inertia. When a high-frequency seismic wave tries to jerk them sideways, they effectively say, "No, thank you." It requires too much energy to quickly accelerate such immense weight. The energy of the wave, thwarted, largely passes around and beneath them. The structure remains almost stately in its refusal to participate in the earthquake's most frantic vibrations. This is not passive resistance, it is an active application of physics, using sheer weight as a filter that strains out the most destructive frequencies. What unites these methods is a profound philosophical shift. Modern engineering often seeks to overpower force with stronger materials. Ancient engineering sought to outwit force with smarter geometry. They viewed the earthquake not as an adversary to be met in a head-on collision, but as a problem of logistics. Their task was to build a network of pathways, converting destructive energy into benign forms and ushering it out of the structure before it could do harm. They worked with physics as a partner, using its own rules to gently neutralize its most violent expressions. This elegant simplicity raises a final, compelling thought. If these principles are so fundamental, could they hold the key not just to preserving the past, but to building a more resilient future? The resilience of a building was often seen as a reflection of cosmic order. Beyond the physics of shifting stones and swaying timbers, ancient seismic design was frequently woven into the very fabric of mythology and spiritual belief. This cultural layer was not a separate decoration, but a powerful framework for preserving and transmitting essential technical knowledge across centuries. The symbolic meaning of a shape or material gave the community a reason to replicate it faithfully, embedding seismic wisdom into sacred stories and daily ritual. Take the iconic Japanese pagoda. Its complex, interlocking wooden brackets, the very joints that allow it to flex during a quake, are more than engineering. In Japanese culture, bamboo is a profound symbol of resilience, bending in the storm but not breaking. The pagoda's flexible frame was seen as an architectural echo of this natural principle. The design was not just smart, it was symbolically correct, a physical manifestation of a valued cultural ideal. This connection ensured that when a master carpenter taught an apprentice how to carve those specific joints, he was passing down more than a technique, he was imparting a piece of the world's philosophical order. The knowledge became sacred and therefore carefully preserved. On the other side of the world, the Inca understanding of architecture was deeply cosmological. Their ubiquitous trapezoidal shapes for doors, windows, and niches solved a critical seismic problem by funneling force downward. But to the Inca, this shape held a much deeper meaning. It represented the Andean worldview, where the wider base was the earthly realm of humankind, and the narrower top was the celestial realm of the gods and ancestors. A doorway was not just an opening, it was a point of connection between worlds, a sacred threshold. This profound symbolism meant that the trapezoid was not an optional stylistic choice, it was a mandatory form for any significant structure. The why of the design, its spiritual necessity, guaranteed the survival of the how, its practical engineering benefit. The technical rule became a cultural commandment, repeated endlessly across the empire in temples, storehouses, and palaces. By embedding seismic principles into their symbolic language and spiritual practice, these cultures created a fail-safe for their own knowledge. The stories told about the bamboo, the rituals performed in trapezoidal spaces, the very identity of the people as builders in harmony with a volatile earth, all served as a living library. If written records were lost or a guild of builders disbanded, the knowledge was not truly gone. It was stored in the cultural memory, in the forms that felt right and true, waiting to be rediscovered by a new generation of artisans who would learn that to build correctly was to build in accordance with the cosmos. This fusion of meaning and mechanics suggests that their greatest innovation may have been social, a way of making resilience inseparable from cultural identity itself. That cultural library of resilience, stored in myth and masonry, is not just a historical artifact. Its shelves hold blueprints for our own future, particularly in places where the earth shakes with terrifying regularity and modern building materials are a distant luxury. For millions living in seismic zones across the developing world, the ancient dialogue between structure and earth is not an academic curiosity. It is a pressing question of survival. Here, the relevance of this rediscovered wisdom becomes starkly practical and profoundly urgent. In regions where access to reinforced concrete and seismic engineering is limited by cost or logistics, these low-tech, high-knowledge solutions offer a viable, life-saving path forward. Non-governmental organizations and visionary architects are now looking back to move ahead, reviving and improving ancient techniques to build safer communities today. They are not advocating for a return to the past, but for an intelligent fusion of timeless principle with modern understanding. Take the humble adobe brick, sun-dried earth, one of the oldest and most common building materials on the planet. Traditional adobe walls can crumble catastrophically in a quake, but by applying ancient insights, that weakness can be transformed. Inspired by the Minoan use of timber within stone, engineers are promoting improved adobe, where a lightweight framework of bamboo or cane is embedded right into the earthen walls. This bamboo lattice acts exactly like those ancient wooden beams, providing flexible tensile strength that holds the wall together as a cohesive unit during shaking. It is affordable, uses locally available materials, and can be built by the community itself. Similarly, the ancient understanding of engineered foundations is being revived through techniques like the rubble trench foundation. This method, directly inspired by the deep gravel beds found under Inca structures, involves digging a trench below the frost line and filling it with compacted, drainable stone. This creates a stable, well-draining base that prevents settling and liquefaction, a simple yet brilliant upgrade over pouring a concrete slab directly onto unstable soil. These methods are more than just cheap alternatives. They represent a philosophy of context-appropriate technology. They utilize local materials, empower local labor, and have a far lower environmental footprint than importing tons of cement and steel. This work is happening now, from the hills of Nepal to the coasts of Central America, where organizations are training builders in these hybrid techniques. The goal is not to construct museums, but to create homes, schools, and clinics that will stand when the ground moves. This movement underscores a crucial point. Our conversation with these ancient builders is not about nostalgia. It is about recognizing that they developed a profound science of resilience through centuries of iterative learning, a science written in a language of stone, wood, and earth that we are only now relearning how to read. By engaging in this dialogue between past and future, we are not abandoning modern innovation. We are enriching it. We are combining the strength of our materials with the wisdom of their principles, creating a hybrid resilience that is both smart and accessible. This approach asks us to see traditional knowledge not as primitive, but as precocious, a vast, untapped repository of solutions that are sustainable, economical, and tested by the one force that never lies, time itself. The ultimate lesson may be that true resilience is not a product we buy, but a knowledge we build and share, a legacy as solid as interlocking stone, passed once again from one generation to the next. Their structures were not just resilient to the earth, but to the passage of time itself. This longevity points toward a dimension of ancient engineering we have only begun to appreciate, its profound and inherent sustainability. In an era defined by a climate crisis and resource scarcity, these millennia-old buildings stand as silent witnesses to a radically different philosophy of construction. They represent a masterclass in low-carbon resilience, where the solution to one existential threat, earthquakes, also provides a blueprint for addressing another, our environmental impact. Every aspect of their design was lean, local, and lasting. The materials were not shipped across oceans or manufactured in energy-intensive factories. Builders used what the land provided: stone from the nearby quarry, timber from the surrounding forest, earth from the very site. This drastically reduced the embodied energy, the total carbon cost from extraction to transportation to assembly. The Inca did not import granite from another continent, they shaped the mountain beneath them. The Roman concrete that still stands used volcanic ash from local deposits, mixed with lime produced nearby. The processing was minimal, often just the work of human hands and simple tools, avoiding the fossil-fueled machinery that dominates modern construction. This localism was not a limitation. It was the source of their strength, creating a deep harmony between the structure and its specific environment. But the sustainability went deeper than just materials. These were passive systems in the truest sense. A pagoda's dancing column requires no electricity, no computer sensors, no maintenance crew to activate during a tremor. It works through gravity and geometry alone, a perpetual motion machine of seismic defense waiting silently for the moment it is needed. The Sandbox foundation under an Indian temple needs no pumps or monitors. The dry sand is always ready to flow and dissipate energy. This passive intelligence means zero operational carbon emissions for centuries of protection. There is no need for backup generators or complex mechanical systems that can fail. The resilience is baked into the form, not bolted on as an expensive, energy-dependent afterthought. Perhaps most strikingly, these structures were designed for permanence, not for replacement. The concept of planned obsolescence would have been utterly foreign. A temple was built to endure for generations, to become an ancestor to the community that followed. This long-term perspective changes every calculation. When you build something to last 1,000 years, you invest more care, you select materials for durability over cheap speed, and you create a legacy that accumulates value rather than waste. Contrast this with much of our modern built environment, designed with decades, not millennia, in mind. The endless cycle of demolition and reconstruction consumes staggering amounts of energy and raw materials, filling landfills and pumping carbon into the atmosphere. The ancient approach asks a different question. What if we built things once and built them so well they outlive us by 100 generations? Re-embracing these principles does not mean abandoning steel or glass, but it demands a fundamental shift in priority. It asks us to design for adaptive reuse, to favor durable, low-embodied energy materials, and to harness passive physics over active machinery wherever possible. Imagine a new generation of buildings that use modern engineering to amplify these ancient truths. Structures with geothermal cooling inspired by subterranean airflow principles. Facades that manage solar gain like the thick walls of a desert fortress. And seismic flexibility achieved through intelligent geometry rather than sheer mass of concrete. This fusion could unlock a new paradigm where resilience and sustainability are not competing goals, but two sides of the same coin. A building that is gentle on the planet in its creation and steadfast in its protection of the people within it during a disaster. The ancient builders, in their dialogue with a volatile earth, inadvertently crafted a response to a crisis they could never have imagined. They left us a manual not just for surviving the shaking ground, but for building a future that is both safer and more sustainable. proving that the most forward-thinking design may sometimes be found by looking thoughtfully into the deep past. This mastery of ancient methods, however, was not without its own profound costs and constraints. To view these structures solely through the lens of their success is to miss a crucial part of the story. Their resilience came at a price, one measured in human effort, time, and a vulnerability to the very societies that created them. Acknowledging these limitations is not a dismissal of their genius, but a necessary step toward understanding what their wisdom can and cannot offer our world today. The most immediate limitation was the staggering investment of labor and time. The polygonal walls of Machu Picchu or the cyclopean fortifications of Masonry represent thousands upon thousands of person-hours. Each stone was quarried, shaped, transported, and fitted by hand, a process that could consume decades for a single temple or palace complex. Grand projects were not the work of a single lifetime, but of generations, with a master builder laying the foundation knowing he would never see the capstone placed. This scale of effort was only possible within highly organized, often centralized societies with the resources to command such monumental workforces. It was a resilience born from immense collective sacrifice, a reality far removed from our modern expectations of speed and efficiency. These techniques were also inherently limited in their application. They were perfected for low-rise, high-mass construction. The logic of interlocking stone or flexible timber frames works beautifully for a 5-story pagoda or a sprawling single-level temple complex. But try to build a 30-story apartment block using only dry stone masonry, and the physics simply fail. The compressive weight becomes untenable, and the lateral forces from wind alone would overwhelm the structure long before an earthquake arrived. Ancient methods were exquisitely tuned to a specific scale of human habitation, one that kept people close to the ground. They solved the problem of horizontal shaking for monumental, but not towering, architecture. Perhaps the most poignant limitation was the fragility of the knowledge itself. While embedded in cultural practice, this architectural wisdom was not immune to the tides of history. Societal collapse, invasion, or radical cultural shift could sever the chain of apprenticeship and oral tradition. The precise recipe for self-healing Roman concrete was lost for centuries. The nuanced understanding behind certain Minoan building techniques faded with their civilization. This loss reminds us that the survival of the knowledge was as precarious as the survival of the cultures that nurtured it. Not every ancient building stood the test of time either. For every Pantheon or Horyuji pagoda, countless others succumbed to quakes that exceeded their design limits or to the gradual erosion of maintenance. The archaeological record is filled with their ruins, silent testimonials to experiments that ultimately failed. These are not marks of inferiority, but of a relentless process of trial and error where each collapse taught a harsh, vital lesson to the survivors. This honest appraisal is essential. It prevents us from romanticizing the past as a lost golden age of perfect building. Instead, it sharpens our focus on what is truly transferable. We cannot and should not seek to rebuild our cities with the methods of the Bronze Age. The demand for housing, the scale of modern infrastructure, and the ethical expectations around worker safety and construction timelines make that impossible. But we can, with brilliant selectivity, extract the underlying principles. The ancient insight was not about using stone instead of steel. It was about managing energy, designing for flexibility, and engineering the interface between structure and ground. These are the timeless concepts. We do not need to replicate the Inca stonework, but we can use advanced materials to create wall systems that dissipate energy through controlled deformation. We do not need to suspend a giant timber pillar, but we can engineer tuned liquid dampers that perform the same pendulum function in a steel frame skyscraper. The goal is adaptation, not replication. By understanding both the profound success and the inherent limits of these ancient systems, we free their core wisdom to inspire solutions that meet the unprecedented challenges of our own time, building on a foundation laid thousands of years ago, but reaching toward a future they could never have envisioned. The principles are not locked in the past, they are actively being reborn in laboratories and construction sites today. This cross-temporal dialogue is perhaps the most exciting chapter in the story of seismic resilience, where ancient intuition meets 21st century material science. The most direct descendant is base isolation, a technology now safeguarding everything from children's hospitals to priceless art museums. The concept is the direct heir to the Indian Sandbox Foundation and the flexible timber frames of Japan. Instead of sand or wood, modern systems use alternating layers of solid steel plates and high-density rubber bearings. These are installed between a building's foundation and its superstructure, creating a flexible interface. During an earthquake, the ground moves violently, but the rubber layers deform, allowing the entire building above to slide slowly and smoothly atop this engineered cushion. The building is literally decoupled from the shaking earth, just as a temple once was on its bed of dry sand. It is the same brilliant logic, translated into a new, more precise material language, protecting surgical suites and irreplaceable artifacts with a principle thousands of years old. Even more futuristic innovations are taking cues from this ancient playbook. Material scientists are developing what are called shape memory alloys, metals that can be bent or deformed under stress but will return to their original shape when heated. This is a high-tech, molecular-scale echo of the flexible wooden joints in a pagoda that flex and then settle back into place. Imagine a structural beam made from such a material within a skyscraper. During a major tremor, it could bend dramatically to absorb energy, then, perhaps using embedded sensors and a small electrical current, actually straighten itself afterward, reducing damage and repair costs. The goal remains unchanged: to create components that yield gracefully and recover, moving from rigid resistance to intelligent resilience. Perhaps the most poetic modern quest is for self-healing concrete, a direct effort to recapture the lost secret of Roman longevity. Instead of merely studying ancient recipes, engineers are now looking at the very patterns of aging in these old structures. They use microscopes and advanced imaging to analyze the fractal-like networks of tiny, healed cracks within 2,000-year-old mortar. This natural healing, driven by ongoing chemical reactions, is a blueprint. Inspired by it, researchers are experimenting with concrete that contains tiny capsules of healing agents or specially designed bacteria that remain dormant until a crack forms, at which point they activate to produce limestone, seamlessly plugging the gap. This is not mere imitation, it is learning from the biological-like behavior ancient builders somehow engineered, striving to create modern materials that are not static, but alive with repair. This vibrant exchange proves that ancient problem-solving is a fertile and far from exhausted ground for radical innovation. It shows that good design is timeless because it solves fundamental physical and human problems. The past, in this light, is not a museum. It is a prototype. It offers tested concepts, a different way of thinking about the relationship between structure and force. Modern engineering provides the tools, the computational power, and the advanced materials to refine and scale those concepts in ways the original builders could never have dreamed. The dialogue enriches both sides, granting ancient ingenuity a new relevance and giving modern science a deeper, more nuanced history. It suggests that the path to a safer future does not always point forward in a straight line, but sometimes curves back to gather wisdom left along the way, ready to be combined with everything we have since discovered. These timeless principles did not emerge from the earth on their own. They were born from the minds and hands of individuals, master builders whose names are often lost to history, but whose legacy is set in stone. Behind every trapezoidal doorway and every interlocking bracket stood a profound human tradition, a lineage of knowledge passed from teacher to apprentice with the gravity of a sacred trust. In medieval Europe, this wisdom was guarded by the Masonic guilds, sworn brotherhoods of stonemasons who encoded their geometric secrets into the very cathedrals they built. In Japan, the Toryo, the master carpenter families, held the intricate plans for pagodas and temples, their understanding of wood's behavior a closely held family inheritance. Across the Andes, the Inca Kamayoks were the state-appointed specialists, experts in quarrying, fitting, or hydraulics, each a vital piece of a larger engineering puzzle. Their training was a lifelong journey, a rigorous fusion of empirical observation and deep craft knowledge. An apprentice did not simply learn to cut stone, he learned to listen to it, to understand which grain would hold under pressure and which would flaw. He memorized complex geometric rules not from a textbook, but through the physical act of laying out a foundation with cord and stake. He absorbed material law, knowing that timber cut in a certain season had more flexibility, or that clay from a specific riverbank would produce the most durable brick. This knowledge was often secretive, protected within guild halls or family workshops. But this secrecy was not about hoarding. It was about preserving the integrity of techniques that meant the difference between a shelter and a tomb. The master builder's role was one of immense responsibility. He was the guardian of a cumulative wisdom, a living library of what had worked and what had catastrophically failed in generations past. His task was to judiciously innovate upon this sacred trust, to adapt timeless principles to the unique demands of a new site, a new patron, or a newly understood seismic pattern. He balanced reverence for tradition with the necessity of invention, ensuring that architectural knowledge was not a static relic, but a living, breathing system that could evolve without breaking its essential connection to the earth. These individuals stood at the crossroads of art, science, and survival. They thought in forces and flows, visualizing the invisible pathways of stress long before the mathematics existed to describe them. Their intuition was a form of highly refined data analysis, built on a foundation of observed cause and effect passed down through stories of triumph and tales of collapse. They ensured continuity in a world of constant change and danger, weaving the thread of resilience from one generation to the next, so that even in their anonymity, their conversation with the earth would never fall silent. The master builders designed their monuments to endure centuries of shaking, but they could not foresee the slow, silent pressures of a modern world. Today, these resilient structures face a paradoxical threat, the very passage of time they were meant to conquer. The earthquakes they were engineered to survive continue their relentless cycle, each tremor accumulating tiny, incremental damage. Yet now, they are besieged by new adversaries, air pollution that eats away at stone, rising groundwater from altered landscapes, and the crushing weight of mass tourism. In some places, simple neglect has left once proud walls vulnerable to the encroaching forest or the scavenging of stones for new construction. This creates a global race against time, a quiet emergency to preserve not just beautiful ruins, but the physical knowledge they contain. The wrong kind of help, however, can be more destructive than neglect. Imagine using modern Portland cement, a rigid, impermeable glue, to repair a crack in an Inca wall. That wall is a dynamic system designed to shift and settle. The hard cement patch would not move with it. Instead, it would create a stiff, unforgiving point that concentrates stress during the next tremor, causing the ancient stones around it to crack and shatter. This well-intentioned mistake can cause irreversible damage, turning a reparable settlement into a catastrophic failure. It underscores a vital truth: to save these structures, we must repair them in the language they were built in. This is why preservation has become a sophisticated collaboration across disciplines. Global organizations like UNESCO partner with national cultural heritage bodies, local engineers, and most crucially, the few remaining traditional craftspeople. The goal is stabilization, not restoration to a false perfection. Teams might carefully dismantle a dangerously leaning section of dry stone wall, cataloging each block like a precious artifact, then rebuild it using the original interlocking technique, perhaps adding subtle, non-invasive stainless steel pins for critical reinforcement. They clear ancient drainage channels clogged for centuries, allowing the foundational systems to function again. They use laser scanning and drones to monitor millimeter-scale movements over time, predicting where intervention is needed before a collapse occurs. This work is painstaking, expensive, and often unseen, but it is a defense of something far greater than scenery. Each stabilized site remains an open-air textbook, a three-dimensional blueprint of seismic wisdom. If we lose these structures, we lose the primary sources for this ancient science. Future engineers and architects would be left with only diagrams and descriptions, unable to feel the fit of the stones or trace the path of a force through a timber joint. This global preservation effort, therefore, is about safeguarding a library of human ingenuity. It is an acknowledgement that these stones hold dialogues we are still learning to hear, and that their silent lessons on resilience are perhaps more valuable now than ever before. From the dancing pagodas of Japan to the interlocking stones of the Andes, we have journeyed through a world where ancient builders turned seismic threats into architectural triumphs. Their legacy is a powerful reminder that resilience often lies not in complexity, but in a profound simplicity, in flexibility over rigid force, and in a deep, listening harmony with the natural world. These timeless principles, forged entirely without metal, stand as a quiet challenge to our modern assumptions about progress. For centuries, we have equated advancement with stronger materials, with more control, with the power to dominate our environment. Yet these ancient stones whisper a different story. They suggest that true advancement might be about smarter design, about intelligent yielding, about building with nature rather than against it. The insights etched into these walls offer us something invaluable, a blueprint for a safer and inherently more sustainable way to build. They teach us that durability does not have to come at the cost of the planet, that a structure can be both gentle in its making and steadfast in its protection. As we face our own era of tremors, both the literal shaking of the ground and the metaphorical shocks of a changing climate, these lessons feel urgently relevant. The past becomes not a distant memory, but a partner in problem solving. Perhaps then, looking thoughtfully back at these conversations between human ingenuity and the moving earth is not a step away from the future, but the most progressive step we can take. It is an invitation to blend the wisdom of the old world with the tools of the new, to create a legacy of resilience for generations we will never meet. If you found this exploration of ancient genius compelling, we would love to hear your thoughts in the comments below. What principle resonated most with you? And for more journeys into the profound mysteries of our past, be sure to subscribe.